kinds of molecules. We're going to go over some basics of the atom and some things you need to know. Let's get started. All right, history of the atom. The main person, or the only person we're going to really talk about is John Dalton, because he came up with a theory that basically said that compounds only have the same ratio. Basically, he said that carbon dioxide, the thing that you breathe out, is always going to be CO2. It'll never be anything else other than CO2. So he's the first person to establish that the ratio of elements inside of a specific chemical will always be constant. Couple of different theories you have to be aware of. J.J. Thomson and his plum pudding model of the atom basically said that the atom looked like this little diagram, which is supposed to be plum pudding. Basically, these are supposed to be your electrons, the red things, and the blue stuff is supposed to be positive charge, which is what allows the atom to stay together, right? If there was no positive charge, these electrons would repel each other and there would be no atom at all. So this is this theory of what the atom looked like. They call this the plum pudding model, as I stipulated. It got removed pretty quickly by Ernest Rutherford and his theory. What Rutherford did was he discovered the proton. So we have J.J. Thomson discovering the electron, and then Ernest Rutherford discovered the proton about 13, 14 years later. And the way he did it, he basically took this canister and he had these alpha particles, which are basically positively charged particles. And what he did, he shot these at this gold foil. And you may ask yourself, how do you shoot them? Well, this whole thing's made out of lead. So the alpha particles are basically radiation. Radiation cannot get through lead. So what he did, he had this little hole in the front of it only, one little hole. That's the only place the alpha particles could escape from. And as a result, that's what forced these alpha particles to get shot. So they got shot at this gold foil, which is made of atoms of gold, obviously. And what should have happened if J.J. Thomson was correct, all these positively charged particles should have went straight through because nothing should have impeded their path. What happened in reality, a bunch of these particles actually either got deflected, either to the sides or all the way back, which implied that there must be something positively charged that it's hitting that's causing it to slow down and cause these reflections or deflections. And that's how he discovered the proton. He knew this thing had to be pretty small because only a small fraction of the particles did it. The majority went through, so that's what led to them hypothesize not only that there was a proton here, but there was a positively charged nucleus where the proton was located, and that thing was what allowed this deflection to occur. All right, presentation information. You're going to see information throughout the year presented the same way as far as the atom is concerned. Upper left is always going to be your mass. Bottom left is always going to be your atomic number. That's what Z stands for, atomic number, is your atomic mass. Your charge is always going to be in upper right, and subscript tells you how many you have. So for example, you may see this, Ca 40, 20, positive 2. That's what you'll see it as. Or you'll see calcium, let's say phosphate, for example, we'll go 3, PO4, 2. So that's where the subscript comes in. It just basically tells you how many of that atom you have. All right, periodic table organization. Metals are on the left of this imaginary staircase. In the periodic table, everything to the left is a metal. That means they're all positively charged. Everything to the right is a non-metal. They can be positive or negative, though they're predominantly negatively charged. You do need to know that certain groups have certain charges. Group 1 is positive 1. Group 2 is positive 2. Transition metals charges are variable. Some of them have multiple charges, so that's why you don't see a listing of charges here. Group 3A with aluminum is positive 3. 4A is weird, so there's no set charges. 5A is negative 3, 6A is negative 2, 7A is negative 1. Noble gases, of course, have no charge because they don't form ions. Isotopes basically are atoms that have the same number of protons, different number of neutrons, which means different mass. So something like chlorine, or we'll do carbon actually. So carbon can be like this, but carbon can also be like this. They're both versions of carbon. The way you could tell they're isotopes, this number is identical. So whenever that number is identical, the element will always be identical that way as well, right? The one thing that's constant for a specific element is the atomic number, the number of protons. So this is two isotopes of the same element because they have different masses. The periodic table, in case you didn't notice, has elements, masses in decimal form, and the reason for that is that what they do, they take all the isotopes of the element. This is, let's say, 20% of the carbon in the world. This is 80%. There's actually a third one, but just going to make this kind of simple. What they do is they multiply the percentage times the mass, so 0.20 or 20% times 13, 14 times 80%. Add them together, and that's the mass you see in the periodic table. So the mass in the periodic table is representative of the masses of all the different versions of the element relative to their abundance, how common they are. So that's what those numbers come from. Ions are basically elements that have charges. Basically, they lost or gained electrons. Protons don't change, and if they do, you have a new element. So all these elements with charges have different numbers of electrons in the neutral versions. They lost or gained them. They're positive, they lost, they're losers. They're negative, they gained them. So this, for example, lost 1, this lost 2, this gained 3, gained 2, gained 1. That's where the charges come from. These are the polyatomic ions. You need to memorize all of these. So basically, you need to know what the symbol is, or the formula, I should say. So this is the formula, the NH4. You need to know the charge, and you need to know the name. So for example, I ask you what is ammonium. You say NH4 with a positive 1 charge. Chlorate, same thing. You would say ClO3 with a negative 1 charge. You do need to memorize all these because they're unique. They're compounds with charges. Compounds usually don't have charges. These are the exceptions. And they do pop up throughout the year. So you being able to recognize them quickly will make your life a lot easier. So you do need to memorize all. These are the common ones you'll see on the AP exam. All right, formula writing basically is based on the crisscross method. Simply put, you write the name, or sorry, excuse me, write the symbol for the element. So magnesium, positive 2, chloride, negative 1. And what you do, you crisscross. Crisscross means this goes here, this goes here. So your formula is MgCl2. For tin 4 sulfide, same thing. SN4 plus, because that's what the 4 represents. Sulfide, negative 2. Crisscross, you get SN2S4. Now, the one thing with the crisscross method you need to be aware of, you have to reduce when the subscripts are reducible. They have a common multiple here, which is 2. So this actually gets reduced down into this, SnS2. Now, why, you may ask? Well, because tin's a positive 4. Basically, what you need to do for any ionic compound is make sure the net charge is 0. So in order to make the net charge 0 here with sulfide, which is a negative 2, I need to have 2 sulfides. Why? Negative 4, positive 4, net charge of 0, I'm done. That's what this represents. If you put this, you are doing it because the crisscross method forces you to, but you have to make the adjustment to get the right formula, which is what this thing is. Iron 2 oxide, that's Fe2 plus, O2 minus. Whenever the charges are identical, just get rid of both and write one of each. So it's FeO. Beryllium phosphate, Be positive 2, PO4 minus 3. When you have a polyatomic ion that you need to have more than one of, you crisscross, but you need to put a parenthesis around the whole polyatomic ion. The reason is you cannot touch this 4. You can't make it become BO8 because PO8 because there's no such thing as a PO8. You can't do PO42, which is the alternative. So what you need to do instead, you bring the 3 down to the Be, right? Then you put a parenthesis around the whole thing because we need to put a number on the outside. Now, if it was a 1-to-1 ratio, let's say it was iron 3 and phosphate, then you would just write FePO4. You do not need parentheses. The only time you put parentheses is if you're putting a number on the outside. So be aware that don't get parentheses happy, which is very common for this. Naming ionic compounds. Compounds made of 2 elements are named the following way. If the metal is from group 1, 2, or 13, just name the cation and then the anion and you're done. So for example, sodium chloride. I just name what I see. I don't need to sit there and figure out charges or anything else. You'll see the difference of this versus the more complex versions. Magnesium chloride, once again, just name what you see because it's group 2. You could also do for, say, hypothetically, we'll do one more. AlCl3 would be aluminum chloride. Same logic. You don't need to do any kind of thinking because it's group 13. Name of an ion always ends with IDE. That's a common rule. If it's a metal from any other group, use a Roman numeral to indicate the charge. The reason is because there's different variations. You need to specify which metal we're talking about. Iron, for example, has two different charges, iron 2 and iron 3. So what I need to do is specify which one I'm talking about. So if I don't put this little 3, I just say iron chloride, you'd be wrong because the question is like which iron are we talking about? So be aware, if it's not group 1, 2, and 13, you do need to figure out the Roman numeral, which is a pain in the butt. There's actually an additional rule for this, ZAC. Zn2 plus, silver, positive 1, Cd. These are the only charges for these three. There's no multiple charge. Even though they're transition metals, they don't have multiple charges. You don't need to put a Roman numeral for it. So if it's 1, 2, 13, or ZAC, no Roman numeral. Everything else, Roman numeral. There's the other version of iron to prove the point. All right, if the compound contains 3 or more elements, use the following. Identify the polyatomic ion, name the polyatomic ion, it's what's attached to. So there's 3 capital letters. That's how I could tell there's 3 elements there. That's ammonium chloride. This is why you need to know your polyatomic ions. That's how you would recognize this. Without knowing your polyatomic ions, you'd just be staring at this. Barium nitrate, so on and so forth. All right, SRO, group 2, so strontium oxide. Pretty easy. Next one, PbCl4. It's not group 1, 2, or 13, and it's not ZAC, so I do need to figure out the Roman numeral. So how do I figure this out? You uncrisscross. The 4 goes here. The 1 goes here. So it's Pb4 plus, Cl minus. Remember, the metal is always positive, Cl is negative. The anion is always negative, so that's how I know this is positive 4, not just 4. And this is negative 1, just not 1. So be aware of that. So this would be lead 4 chloride. All right, next one, group 2. So good news, calcium nitrate. Because group 2, I don't need to sit there and figure out the charges. So if it's not one of the transition metals, then you don't have to worry about the whole, crisscrossing and doing all that stuff. You just name what you see, which is a lot easier. All right, naming binary covalent compounds. These are compounds involving 2 nonmetals. So 2 things from the right side of the periodic table. So that name is always ending in IDE as usual. Prefix used to indicate how many of each element is the formula, but mono is not used for the first element. So you don't call this mono carbon monoxide, you just call it carbon monoxide. So don't use mono at the beginning of a name. You can use it for the second element, but you can't ever for the first element. You just name the element, and you're implying there's one of it when you don't put a prefix in front of it. Different prefixes that you need to memorize are these. There's no way around it. The only one that's kind of weird, I guess, is tetra. The rest, they're basically from geometry, so they're not completely new. All right, this one, di, phos, for us, because there's 2 phosphorus, right? Pent, oxide. When there's a vowel in the prefix, so penta, and there's a vowel at the beginning of the element name, you drop the vowel for the prefix. So instead of calling this pentaoxide, call it pentoxide. Cl2O7, there's 2 chlorines, so that's dichlorine. And there's 7 oxygens, so once again, hept oxide. All right, question, write the formula for each of the following. Carbon dioxide, that's 1 carbon, 2 oxygens, so CO2. Tetraphosphorus. Trichloride, that's 4 phosphorus, 3 chlorides. Oops, sorry. 4 phosphorus, 3 chlorides. Don't know where I put that from. Pentacarbon, C5O. Because pentacarbon, 1 oxygen. That's how you write it. All right, solubility rules are a big deal. So you need to know the rules for determining solubility. Precipitation reactions, what solubilities are based for. Basically, precipitation means forming a solid. So when two ions get together, some of them form solids, some of them don't. So if they like each other, they form a solid. If they don't like each other, they just stay apart. Uh, the solubility always tells you which ones want to stay together, which one do not want to see each other. So soluble, rule one. The rules are hierarchical, or in hierarchy, I should say, any hierarchy, meaning the rule one takes priority over rule two, which takes priority over rule three. So the first rule says that these are the things that are soluble. Ammonium, acetates, perchlorates, alkali metal, which is group 1A, and nitrates are always soluble. Always, not sometimes, always. So that means that anytime you see these, the compound's going to be soluble, call it a day. Easy way to remember it, I am a soluble pan. Notice the capital letters represent the different components: ammonium, acetate, perchlorates, alkali metals, nitrates. So those were always soluble. So if you ever see those, the compound soluble, move on with your life. When rule one does not apply, compounds having anions with a -1 charge are soluble unless OH or Br minus, I minus, or chloride is involved, or brickle. So anytime you have a compound with a -1 charged ion in it, you're going to assume it's soluble. The only time you look at it carefully if it's one of these four. If it's all brickle, you got to look at it carefully to see if it's soluble or insoluble. So predominantly -1 charged compounds or ions in a compound indicate it's soluble unless one of these four are involved. And if one of these four are involved, here are the rules. Hydroxides are only soluble with alkali metals, calcium, barium, and strontium. So the only time a compound involving hydroxide is soluble is if the cation is an alkali metal, calcium, barium, and strontium. If it's anything else, it's insoluble. So it's going to be a solid. Hydroxides don't like alkali metals and CBS. So here's an easy way to remember it. So don't like means that they don't form solids with alkali metals or CBS. For chlorides, bromides, iodides, they only form solids with these three. If it's anything else, so NaCl, PbCl4, not 2, 4, soluble, soluble. If it's one of these, it's going to be insoluble. It's going to be a solid. So brickle is a happy solid. So Bri and Cl form solids with just these three. And that's it. All right, compounds involving anions with a -2 or -3 charge usually are insoluble. So if you have to guess if there's a compound with a -2 or -3 anion, you can assume it's insoluble. The only time you have to look at it carefully is if there's sulfate involved. Sulfates are usually soluble. So if you have a compound with a sulfate, typically they are soluble. The only time it's insoluble is with these four. So calcium sulfate, lead-2 sulfate, barium sulfate, strontium sulfate, those are all insoluble. Anything else is soluble. So sodium sulfate, magnesium sulfate, you can go on and on. All those are considered to be soluble. So easy way to remember that, sulfate is a solid cartoon on PBS, which means a sulfate forms a solid with PBS, and of course C for cartoon, so calcium, lead, barium, and strontium. So how to approach questions involving solubility? First thing you want to do is look to see if the cation is ammonium or group 1. If it is, it's automatically soluble. Move on with your life. If the above does not apply, focus on the anion. Is a -1 charge? Is a -2 charge? -3 charge? That's how you'll determine your solubility rules. So that's the way you would approach it to be the most efficient possible. All right, determine if each of the following is soluble or insoluble. Magnesium sulfate. So remember, sulfates are usually soluble. When are they insoluble? Is with calcium, lead, barium, and strontium. So this would be obviously soluble. Barium chromate. Chromate's a -2 charged anion, so that's going to be usually insoluble. Remember, if you have to guess, -2, -3 anions are usually going to be insoluble, so barium chromate will be insoluble. HgCl2. This is not mercury 1. Mercury 1 is Hg with a subscript of 2. So this is mercury 1 chloride. This is the one that's insoluble. This one that you're seeing in front of you is soluble. So make sure you understand that the mercury 1 has a little subscript of 2. It's just a little quirk with the way it's written. Magnesium hydroxide, if you remember, it's a group 2. It is not one of the exceptions, so it's going to be considered soluble. Barium sulfate. Remember, sulfates usually are soluble, but with barium, it's actually insoluble. PBS, -2, right? Notice that none of these were ammonium or group 1 so far. So as a result, we approached it the way we did when we looked at the anion. So for this one, we don't look at the cation, we look at the anion, -2. -2s are insoluble, so that's what we're going to go with. Not group 1 or ammonium, so focus on the anion. -2 charge, so it's going to be insoluble. Once again, same rule, focus on the anion. -3 charge, it's going to be insoluble. All right, types of reactions. You have combination reactions when you go 2 to 1. Basically, when you have a single product, it's combination. So anytime you see a single product, it's those combination reactions, also called synthesis. Here's another example, single product. The reason you want to focus on the product, not the reactants, because you see here, there's a compound and a compound producing this, but here it's an element, and this is an elemental compound. So that's why you don't want to focus on the left side, focus on the right side. Decomposition is the opposite. You have a single reactant instead. So anytime you see a single reactant, it's always going to be decomposition. Single replacement is when you have a single element in a compound and they trade places, the cations do. So this and this trade places. So whenever you see that, it's called single replacement. You can see the zinc goes alone, magnesium goes into the compound. Double replacement, you have two compounds, and what they're basically going to do is the cations are going to trade places. So single replacement, cations are trading places. Double replacement, cations are trading places. So there's some similarity there. So you can see silver and potassium traded places. Combustion, you're burning. So anytime you see a O2 on the reactant side, it is combustion. You also typically get CO2 and H2O as products. So let's identify each of these. We have a single product, so that's going to be obviously combination. You have two compounds. So what's going on? Are they trading places? Sodium and hydrogen seem to be trading places, and that's exactly what's happening. So it's a double replacement reaction. It's a tough one to recognize. Here you have O2 as a reactant. That's going to be combustion. You also have CO2 and H2O as products, so it's a double bonus. Last one, you have a single reactant. That's going to be decomposition. All right, Ionic equations. These are basically equations showing just the ions or just the chemicals involved in the actual reaction, which is typically going to be precipitation, but not always. So molecular equation is basically you're writing everything. Nothing is omitted. Everything is there. This is all the chemicals that were involved. Ionic only shows the chemicals actually reacting. So if you notice, only this is being produced, right? This is the only product. So the only chemicals I'm interested in is Ag and Cl. KNO3 are gone. They're not part of the Ionic equation because they're not actually involved in the reaction. They're what we call spectator ions. They're in the solution, but they're not involved in the reaction. So they're just there, but they're not involved, so we don't acknowledge them. We don't write them into our Ionic equation. So be aware they are still there, just you can't see them. So here's an example. Silver nitrate reacts with sodium chloride to produce silver chloride. Here is your net ionic. Notice what I did. I got rid of the nitrate, got rid of the sodium. Why? Because they're not involved in the reaction. So when you're doing net ionic, it's based on the solubility rules. First thing you need to realize is silver and nitrate. These are both ions. They're soluble, so you have to break them apart. So you would actually sit there and write Ag plus NO3 minus if you want to go through the extra step. This would be Na plus. This is soluble as well, right? Group 1 and nitrate, so soluble. So these broken apart. And what you're doing is a double replacement reaction. Silver gets together with chloride, sodium gets together with nitrate. But because nitrate and sodium don't produce anything, they're called spectators. We get rid of them, and we're left with just this Ionic equation. Types of Ionic equations, you have acid-base reactions. You do need to memorize all these strong acids, so I suggest doing it quickly. These are all your strong acids. There are only 1, 2, 3, 4, 5, 6 of them, and you want to memorize them as quickly as possible because everything else is weak. So if you know your strong acids, you also know all your weak acids. So 2 for 1. Bases, strong bases are compounds composed of hydroxides or group 1 metals, and these. So group 1, like sodium hydroxide, lithium hydroxide, along with calcium, barium, and strontium hydroxide, those are all strong bases. Everything else is weak base. There's a couple of exceptions, but for the most part, that's pretty accurate. All right, so how to write Ionic equations for acid bases? The strong acids involved, break it apart. If it's a weak acid, don't. What that means in English, HCl is a strong acid. I can't write it together. If it was a weak acid, like let's say acetic acid, you'd put it together. So that's how you would write it. But if it's a strong acid, do not write it together. Write it apart. Break apart the cation and anion so you can see what's going on a little bit better. This is a strong base, so I'm going to break it apart as well. Here you can see the double replacement occurring. Na gets together with Cl, H together with OH, producing H2 and NaCl. Here, what we're going to see is the actual reactions with the complete ion. So here, this and this produce water, which is a molecular compound. We can't get rid of it. What we get rid of here, in case you didn't understand how you're getting rid of these ions to begin with, if it's the same ion on both sides, you cross them out. If it's not, you can't. H plus on this side, H2 on this side, I can't cross those out because they're not the same form. That's the way these work. So H plus OH minus plus H2O is called your net ionic equation. This is a strong acid, strong base, net ionic. This is always what it will look like. Any strong acid and base will have this as its reaction every time because the cations go away. So be aware of that. Not the cations, but the other two ions involved that are not involved in the reaction. All right, oxidation reduction reactions. Oxidation is when elements lose electrons and become more positive. Reduction is when an element gains electrons and becomes more negative. What does that mean in English? Well, best way to know is to take a look at it. I should actually go back and let's do a reaction. Let's do H2 plus O2 produces H2O. Let's balance it real quick just for fun. All right, so oxidation states. We're going to get into what oxidation states are, how to figure them out in a second. So I'm just going to give you a shortcut to it. Diatomics oxidation states are always 0. So this is 0, 0. Oxidation state is a fancy way of saying charge. So the charge of each of these are 0. For H2O, O is a -2 charge. H, because it's a -2, whatever this thing is has to be a +2. This becomes +1. You'll understand how to do this in a second. We're going to go over this in more detail. But for now, just accept these are your oxidation states, right? 0, 0, so 0, 0. So these are my oxidation states. Oxidation means it's losing electrons. So what's losing electrons here? Well, whatever is becoming more positive is losing electrons. So which one of these is becoming more positive, the hydrogen or the oxygen? Well, H is going from a 0 charge to a +1. That's becoming more positive, so this is considered oxidation. In the same respects, O is going from 0 to -2. That is considered reduction. So that's how you determine oxidation and reduction. All right, so let's go into figuring out these charges in a little bit more detail. So first off, atom of an element, not an ion, has an oxidation state of 0. So Fe, 0. Na, 0. Anything that you see by itself without a number up here is going to be a 0. So if you see a number in the upper right-hand corner, that's the charge, that's the oxidation state, great. If you don't see it, the charge is 0. So these are all zeros. Oxidation state of an ion is the same as its charge. So if you see a number in the upper right-hand corner, that's the oxidation state. Oxygen is always going to be -2 unless it's in this compound, hydrogen peroxide. Here, it's a -1, not a -2. So anytime you see H2O2, you need to know O is a -1. Otherwise, O is always going to be a -2. Fluorine is always a -1. Hydrogen is always a +1 in covalent compounds. Like up here, this was H2O, I should say. That's a covalent compound, right? Both nonmetals. So that's going to be a +1 for the H. All right, so let's go over them. So when you see a crazy compound like this, what you want to do is start with the ones that are part of the rules. So O is part of the rules, right? So that's a -2. So there's 7 of them. So -2 times 7 gives me a -14 coming from the O. Chromium, we have no idea. There's multiple charges, but potassium is group 1. Group 1 is always +1. So if you have an element from the periodic table as a constant charge, like group 1A, 2A, 3A, then obviously your nonmetal groups, which is group 15, 16, and 17, you can use those charges. You can shortcut it. For potassium, it's always a +1. But what I do is I put the individual charge in the bottom, and I put the overall charge coming from the element on top. The top is accounting. The bottom is the number I'm interested in. So there's 2 Ks, so this is going to be a +2. So my net charge in this compound has to be 0. If this is -14, this is +2, this has to be a +12. Why? 14 positive and 14 negative gives me a net charge of 0. So to get my chromium's charge now, I'm going to do +12 divided by 2. So you divide the charged overall by the subscript. So it gives me a +6. So these are my oxidation states. These are the numbers I'm interested in. The top is just there for counting. We don't do anything with it. So be aware of that. KMnO4, same thing, -2, right? 4 of them, -8. Mn, transition middle, no idea. K, +1, because there's only one of them. So what does the Mn have to be? A +7. And 7 divided by 1 gives me 7. So here's my oxidation states for this. For this one, -2 times 3 gives me -6. So this has to be a +6, right, to give me a net charge of 0. 6 divided by 2, +3. So those are my oxidation states, +3, -2. O, -2. Fe has to be a +2. When there's 2 elements, you can figure out the charge of the cation pretty quickly. So this is +2, so those are my 2 charges, +2 and -2. F, remember, is always a +1, according to the rules, so this is +2. O is a -2 times 2, so -4. So as you have to be, well, to make this whole compound to be 0, has to be a +2. And that's what happens, because 4 and 4 gives me 0. O, -2. V has to be a +2. So those are my 2 charges. Here, O, -2, which is a -4 charge. Mn has to be a +4 divided by 1, +4. O, -2 gives me a -6 charge. And then you look and you're like, what the heck? There's 2 ends. How do I figure this out? So when you see 2 polyatomic ions like you do here, the best thing to do is break them apart. So we know this is ammonium, has a +1 charge, and we know this is nitrate, which has a -1 charge. Now I'm going to deal with them individually. H in a molecular compound is going to be a +1, so this is going to be a +4 coming from the H. N has to be a -3. Why -3? Because -3 +4 gives me a +1 charge. So those are my oxidation states for those, is -3 and +1. For NO3, I'm going to do it here so it doesn't get too messy looking. O is -2, so that's -6. So what does N have to be? +5, because 5 minus 6 gives me -1. So those are my charges for it. So if you have 2 polyatomic ions, break them apart, it'll make your life easier. All right, organic chemistry study of carbon-based compounds. Functional groups, you need to memorize all these. There's quite a few of them. This is not the list of them. There's some of them are functional groups, but you don't have to memorize all these different variations. We'll get to the ones in a second. All right, first one you need to know is alcohol. So anytime you see OH without a carbon double bond to O somewhere here, you just call it an alcohol. If you see carbon double bond to O, it becomes something else. It becomes carboxylic acid. But for all these, you notice there's no double bonded O, right? So these are all alcohols. That's how you recognize alcohols. So if you see OH without a double bonded O to carbon, it's an alcohol. Ethers, what you're looking for is Coke, C-O-C. So anytime you see Coke, you have an ether. Quickest way to recognize it. Doesn't matter what the other elements are, but anytime you see an O, look in the left, look in the right. If there's carbon, it's Coke, you have an ether. Carbonyl groups are basically, these are the double bonded O's, and there's different variations for it. So if you have a double bonded O with an N attached, it's an amide. R is a chain of carbons. It could be CH3, it could be CH3, CH2, it could be whatever. It doesn't matter. It just means a bunch of carbon hydrogen combinations. The number is irrelevant. What you're looking for is basically look at the middle, or look where the carbon double bonded O is, and see what's on the right, see what's on the left. So on the left we have a carbon chain, great. On the right side we have an N, which means it's an amide automatically. Here we look at the left carbon chain, right hydrogen, aldehyde. That's in comparison to down here, we have carbon chain. You know, this is a different carbon chain. R prime means a different carbon chain. This could be like CH3, for example. This could be CH2, CH3. So whenever you see that, if you see left and right carbon chain, ketone. But if you see carbon chain and hydrogen, aldehyde. Here, carboxylic acid, remember the alcohol? Remember we said if it's double bonded O involved carboxylic acid, that's what I'm referring to. So there's your carboxylic acid, double bonded O to OH. R just means, once again, carbon chain, doesn't matter how many. Ester, here's your cocoa, carbon chain. So there's a C here somewhere, right? O-C-O, cocoa, ester. Estee Lauder, Coco Chanel. I don't know if you know the affiliation, but that's who created it. So easy to remember, it is cocoa is an ester. And let's go over it individually. So aldehydes, once again, carbon chain, hydrogen with double bonded O. There's your aldehyde. Carbon chain, off the double bonded O. That's a ketone. Carboxylic acid, you have a carbon double bonded O, you have an OH. Doesn't matter what's to the left, it's carboxylic acid. You will often see it represented as this, so be aware of it. On the AP exam, they love to write it as this. So if you ever see COOH, carboxylic acid, you have to know that this is a double bonded O and there's an OH there. Ester, there's your cocoa, COCO. Amide, there's double bonded O, carbon chain, there's your N. That's amide. That's different than amine. Amine does not have the carbon double bonded O. That's the difference. So if you see carbon double bonded O with an N, amide. If you see N with a carbon or carbons, that's amine. All right, answering FRQs, use claim evidence and reasoning when you're trying to answer it. Oftentimes students really don't answer the question being asked, and they don't provide enough information for the grader to give them full credit. So if you just use CER, it kind of shortcuts it. So claims specifies your answer. So here you're just going to answer the question whatever they're asking. Your evidence is either going to explain it verbally or mathematically why that answer is whatever it is. So you do your computation or you do a verbal explanation. Wonderful. The last thing you need to do is use reasoning to explain why that piece of evidence helps explain the claim. So when you're doing a question, always ask yourself, can the grader ask why at the end of this? If they can ask why, that means you left something open. You need to close all the loops. So when you're answering questions, make sure you write what the answer, whatever you think it is, provide either verbal or computational proof of whatever that answer is. You can't just say, here's my answer and call it a day. They'll give you 0 points. And then try to connect the evidence to the claim. Like, this is why this is the answer. And we'll go into more detail how to do those as we progress through the year. So here's an example. Is the above an acid-base redox or precipitation reaction? So what are we looking for? It's not redox. Even though there's charges involved, no charges are changing. You can't recognize that without doing the oxidation states, but trust me. There's no precipitate because there's no solid being produced. So what we have left is acid-base. So claimed reaction is acid-base. Great. Evidence, the ammonium ion is donating a hydrogen ion while the hydroxide ion is accepting it. So all you're doing is citing what you're seeing that helps you identify as an acid-base reaction. But that doesn't explain why this is a valid way of looking at it. You got to go into the theory, the science. What lets you assume that because there's a acid and there's a base, this is actually going to be an acid-base reaction like this, or that there's a donation of hydrogen, there's an acid-base? That's based on this. According to Bronsted-Lowry theory, an acid-base reaction consists of the donation of a hydrogen from the acid to the base. So now you bring in the theory. So this is where the reasoning comes in. That's where you incorporate the theory. Your evidence is what you're seeing in the question or what your math is. And then your reasoning is why is that math or why is that verbal explanation valid. So keep that in mind as you're doing questions throughout the year. All right, and that was the first unit.